Zhao Shen say you want to extend assignment. Do you guys want to extend? What? No problem. Until what day? Yes. Sunday. Zhao Shen suggest Sunday. Huh? Today. Sunday. Huh? Monday. Exam already, eh? Cannot too long. You need to do revision. Huh? That one is different course. Assignment, yeah. Tuesday, huh? 哦，shit， sorry 啊，这样你们可以提早你们自己的 deadline。So what day？ 啊 ？What day？ 呀，是我就是这个情况。So 你们呢？你们觉得呢？招生讲Sunday啊？什么 ？extend assignment Sunday 是这样啊？Sunday 还是 Monday？ 啊？所以罗号要什么？所以要 Sunday。OK，Monday 啊，Monday。什么？要不要讲？不长。不长。Okay, Monday, so Monday, so if you want to hand in faster also can, but we extend to Monday. Then you need to do revision already. Okay. 我发现每次巧彤很早交哦，巧彤，你是很早交每次。我发现你前几次都很早交，1、2、3，我 extend 你都没有 extend 的。有，我发现我开机器前。所以我喜欢 ，I like it。Yeah， 其实这个班我都很喜欢的，其实真的。不会挑拨离间，就是 like 喂，要打仗啊，就是说 like 你们只要努力做都 OK 了，其实呀，你们努力做都 OK 不要写这些垃圾上来就可以了，呀，帮我审查垃圾才交给我，呀，OK， yeah。啰嗦还可以了，但是不要太乱，太乱的话读不清楚。有时候有些人写到很 messy 很乱，然后就很难读。哎，金生呢？不知道。Okay, so yesterday we mentioned about so let's recall first. Yeah. Let's recall a few important definition. So first definition we want to recall is a function f, okay, between x ex and y ey, okay, is continuous. OK， 谁可以跟我讲一下open continuity 的 definition 吗 ？Open continuity definition. Where do you start? For every open subset? Open subset U in Y. The pre-image of U is also open in X. should we use in 还是什么？I don't want to say subset. Okay, open in X is okay because there's no worry about it. Okay. Then yesterday we also defined continuity at a point, right? Okay, how about at a point? So function f x to y again is continuous at, let's say, a point P if what? For every open subset that contain P in Y. Wait, 我在写什么东西 ？Contain P in Y. F what's the statement 啊？忘记了。Pre-match of what? Pre-match of you live in where? You sure? 会不会太大哦？我刚才是这样想，感觉好像不太对。check 一下，感觉不太对，感觉太大了。好像是，好像是，好像是哦。因为 epsilon delta 里面的 definition 是这样：for every epsilon there exists a delta。这边 for every epsilon 了就没有 delta 了。So delta 发生在哪里？There exists a open，叫它什么？叫 open O 啊？No, it's not. No, the pre-image I think is living in some pre-image. Sorry, living in some open set. I guess there exists some open O in X such that F inverse of U should be living in O. Okay, let's check this. Sorry. F inverse P live in O. Well, I mean, if you make sure that F inverse U, yeah, P is in U, then obviously it's okay. But I think we have another way. Let me see. Are we doing the right thing or not? So for every open set, P can contain hey, I think a bit stupid here. Can anyone find something wrong here in this definition? Yes, P is in X. How come P go to Y? Something wrong here. So yeah, get rid of this. Something wrong here. So continuous at X, but this one is for every open, not just open set, actually open neighborhood. V of HP. Okay. So your epsilon need to build around FP first. Okay. Then there exists another open neighborhood. Just open neighborhood is enough. No need to be open set. Okay. Of P such that FU is in V. Yes. Yeah. Open neighborhood not necessarily open set. Yeah. Okay, so this one is continuous at P for open set. Okay, now we're going to define homeomorphism. F going from X Y is an homeomorphism if both F and F inverse are continuous. Okay, so homeomorphism is a bijective continuous function. Okay, moreover, the inverse is continuous. Okay, usually bijective continuous function just means that that continuous function is bijective, but it's not guarantee whether the inverse function is continuous or not. Okay, if you require the inverse function to be continuous, then it's called a homeomorphism. Okay, homeomorphism. So make a remark here. Actually, you can prove it on this definition here. F is a homeomorphism if and only if F is a bijection such that Fu is open if and only if U is open. Okay, because if you continuous in one direction, right, it just requires you that the inverse function is open, but you have both way continuous for now. Okay, so you can deduce that it is U is open if only if Fu is open. So meaning what? Homeomorphism will send open set to open set. Okay, homeomorphism send open set to open set. Okay, so if it is open on one side, then it is open on the other side also. So let's say you got two length here, X and Y. Then you have an open set in U, and then you send it across, you'll get another open set here. Maybe to make it very open. Okay, and then you go back forward, it's still open. Okay. So what kind of map that have you studied? Do this kind of preservation of property? By homomorphism, right? Group homomorphism, right? You preserve group structure. And then ring homomorphism, you preserve ring structure. Linear transformation, you preserve vector space structure. So this homeomorphism here preserve topological structure. Okay, you preserve topological structure here. Okay, so so even though you didn't realize, actually we are putting topology on group and rings now, right? Correct or not? Because you consider the metric spaces. R has a group structure there. Okay. So there's an idea called topological group. Okay, topological group. Okay. Yeah. Okay. Huh? Let's give some examples. Some examples. So very easy example is, for example, translation. Okay, translation in real number line is homeomorphic. Okay. What's the inverse? X minus T. Okay. Yeah, both of them are translation. If you prove one of them is continuous, obviously the inverse is also continuous. Maybe give one non-example, pretty important non-example here. So the claim here is, so this is non-example. A bijection f from x to y can be continuous without being a homeomorphism. Okay, meaning the inverse might not be continuous. Okay, so how on earth we're gonna build this? So what's the strategy here? What's the strategy here? So you start with a continuous function. Okay, you have an open neighborhood y, open set in y, but when you look at the pre-image, it's not open. It's open. Okay, but if when you consider the inverse, okay, you consider an open set in the domain. Okay, in the how to say, not domain. Let me think. It's the domain of your f, but it's the co-domain for your inverse function. Okay, and then you look at the pre-image of your inverse function. It's not open. Okay, can you create something like that? Okay, so our goal is to create something like that. If you go the other direction, you don't have open pre-image. Okay, so the idea is this. So let's consider f from this half open closed interval here. Okay, we're going to map this into S1. Okay, very simple object, the object that you have seen in even calculus 2. Okay, so on one side, you just have a half open interval here, 0, 1. And then on the other side is just circle the center at origin. So what do we do here? The usual parameterization you're going to see here. T going send to cos 2 pi t and sine 2 pi t. Okay, this map is easily a bijection. Okay, it is a bijection. Okay, no? Okay, so you just take this line here, go and map it like this. Okay, where do you start in particular? Which this point here? 0 sends to where? 0, 0. 没有 0 这个点啊。S1 is on XR2. So which point? Cos 0, sine 0, what do you get? 1, 0. Okay, you get to this point here. So here is F0. Okay, and then you can imagine, or you just plug the value in. So you can like stick your line around here. Okay. Huh? Okay, ma? Okay, ma? Because this is a fraction of 2 pi. Okay. If I take this one in, what happens? If I take one in, what happens? Cos 2 pi and sine 2 pi, what do you get? 1, 0. Okay, so you go back to F0 point. So that's why we don't repeat we throw away this point here. It's enough to build this circle already. Okay? Make sense? Okay, so this is a bijective function. Okay, or you can find the inverse. The inverse, just take cos inverse and sine inverse, right? Yeah. This is a bijective function. Okay, but the claim is unfortunately F inverse is not continuous. Okay, so if I want to show that F inverse is not continuous, what do I need to do? I need to take an open set in half closed interval 0, 1, and then show that the pre-image of this F inverse is not open. We are not open in this S1 here. Okay, which open set you can consider? Which open set you can consider here? Maybe I can give you some hint here. Here we could consider a subspace topology already. And because you can see that half closed interval actually is not open inside the real line. Okay, so you can consider subspace topology. Okay, to look for the open set there. So if by using subspace topology, right, how to look for open set in this space then? All the topology there should be open set from R intersect with the subspace. So in particular, right, you can look at an open set around 0. Around 0 here. So meaning we just take this part up to an open interval here. Okay. What's the pre-image under the inverse map here? Sorry, half circle. Half circle. Well, I mean, obviously, if you take half of it, it's half circle. But from where to where? Should be from this 0, 1, right? Sorry, 1, 0, up to some point here. Right or not? But if you look at this subset here, okay, maybe I use another color. Looking better? No. This color. Okay, so if you look at this set here, this is the pre-image of this open set. Is it? Okay, so let me draw this right better. Okay. Is it open or not in S1? As a subspace topology, right? As a subspace topology, how do you find open set in S1? You need to take the open set in R2, intersect with S1. Okay, but open set in R2 looks like what? Euclidean topology. Open ball, right? Open ball. Okay. So if you take open ball, right, and intersect this subspace topology, what can you see here? You will always include something extra. You always include something extra. If you say, oh, I don't want this extra stuff, okay, I make it on that F0, but then you will throw away that point already. Yeah, you will throw away F0. So no matter how, if you want to include this F0, right, you have to go a little bit further. Then it's not entirely the inverse image of this open set here. This open set around 0 on the real, on the hard close interval. Okay. Okay. Does that make sense? Okay, so you cannot use open set to build your pre-image under this inverse function here. Okay, I read out the full argument inside the lecture, but you can check it out later. Okay, but although you might see that, oh, there's no homeomorphism, right? But actually, this is a subject that people study in algebraic topology. Okay, how to build a circle using a line. Okay, so we just what do we take here actually? Yeah, we take a line. Okay, we take a dot here. We take a line with an empty hole here. Okay, and then we just glue it. Well, we just glue it at that point. Yeah. So actually require something called gluing method to do this. But I think this is one of the gluing methods already. Yeah. Okay, we managed to glue the line together. But we won't do this in this class. This will be done in algebraic topology. Okay. Okay. Just I want to demonstrate to you that there's continuous function, bijective continuous function. There's not a homeomorphism. Okay. Right. So in general, how to build a continuous function? I'll go rather fast in this part here. I'll leave you to check all the details, but not very important actually. Okay, so how to build a continuous function in general? Okay, let's put a theorem. There's few ways, right? First thing you should know is about constant function. Okay, what does constant function do? If you have a domain, okay, and you have a codomain, okay, so what do you do here? You send everything to a point. Okay, this is a constant function. Okay, you send everything to a point x1. Okay. Second, so you should check that this is a continuous functional. Okay, so you need to form open set in your codomain and then check that pre-image is open. Okay. Next is inclusion. Okay. Inclusion is also continuous. Okay. What is inclusion means? Okay. So you have x. Okay. And then you have y. Okay. What do you do is you just send every x injectively. Okay. Injectively into y. Okay, you send it injectively. Maybe the shape can change, but if I name this as I, this is just IX. Okay, maybe the shape could change, but it's injective. Okay, this is continuous as well. The next part is composite of continuous function is continuous. Okay. Similar to what you know from analysis. Composite of the continuous function is continuous. Okay, if you have continuous function, you can compose them. And then what else? You could restrict. Okay, restrict the domain. What do you mean by restrict the domain? Restricting the domain. Okay, so let's say you know that your f is continuous on x. Okay, so the f is continuous x. Yeah. Okay. Then you can just look at a small subset of x. Okay. And then you could ask, how about I define a f on A? Okay, is it still continuous or not? Yes. Okay, it is still continuous. Okay. Using subspace topology. Okay. So you can restrict your domain, still good. Okay. Other than that, what can you do? You can do something on your range also. Okay, you can also restrict or expand your range. Okay, expand the range. Okay. So for example, let's say your x is like this, and then your y is like this. Okay, so you have a continuous function already. Okay. Then you can look at a smaller z such that your fx actually live inside here. Okay. Then maybe you can call this map a new G. Okay. This G has a domain in X. This G has a domain in X and codomain in Z. Okay. It's the same map, but I changed the codomain. Still works. Still can do it. Where you still can do it. The other thing is, if I know that my function is continuous, function is continuous on y, then I can define it to be a larger codomain here. Let's say Z. Okay. This H, let's say we call this H, is still continuous also. Okay. Anyone think that this is extra? 就觉得很多余嘛，感觉很多余哈。但是 but sometimes when we do proof, right, we might want to decrease our range, or we want to consider in a larger spaces. Then you will naturally ask this question: is it the same? Okay, the function changes already. Actually, you might think that domain didn't change, but the range changed, the codomain changed. Remember, your continuity definition is defined based on your codomain. You need to check every open subset inside your codomain. Okay, so if you define your H as a larger codomain already, maybe you have more open set to check already. Where you have more open set to check. Okay. Okay. But both of these, one thing you need to be sure is Z is a subset of Y for the first case. For the second case, is Y is a subspace of Z. we don't simply change the topology. Otherwise, it's not comparable later. Okay, it's a subspace. Okay, we don't simply change the topology. Otherwise, nothing to compare. Okay, F is all about locality, so local formulation of continuity. Okay, so this one is quite interesting here. It says that if you have a map that's continuous from X to Y, okay, if you know that this map is continuous, and somehow you know that I can split, okay, I can split this X into union of open set. In particular, you can use your basis element. Okay, if it's generated by basis, you can use your basis element. Then from which part? Part D, right? We can restrict our F, right? If we restrict our F to this 4 part here, are they still continuous or not? Yes. Okay, the answer is yes. It's still continuous. It's still continuous. Okay. All these are good exercise to try and do. Show that they are continuous. I have done it in my lecture notes, so you can check. Okay, the next part is gluing or the testing lemma here, or theorem. The testing lemma. Okay, so what's testing lemma here? So let me write down. So let X be A union B, where A, B close in X. Okay. Let's let A from A to Y and G B to Y be continuous. Okay. So do you have a imagination in your mind already? So let's say we have a A. Okay, let me draw it out. If I have a A like this, okay, and then we have a B, let's say like this, and then X is the whole thing, and I have a F. We have a F mapping out from A, okay, to somewhere Y, or maybe I'll try to draw this one. So a direction to Y, okay. So let's say to Y, and then B also to Y. Okay, so here using F, here using G. Okay, so if let's say Fx equal to Gx, agree on the intersection. Okay, if they agree in the intersection here, then actually we can form a larger continuous function. Okay, so how do we form this larger continuous function here? So we can define get a continuous function h, okay, from the whole x to y. What do we do here? We will define it to be fx if x is in A, gx if x is in B. Okay, there are a few things to check here. What? So from this reading here, right? How many things you need to check? 1,000. What thing you need to check here? Uh-huh. Uh-huh. What thing you need to check here? What do you get? You get a continuous function. So you need to check that this function is continuous. But there's more important thing you need to check. whether this is really a function or not. Why? Why is this important? Because A intercept B could be non-empty. If it's non-empty, what does this X tell you? If it's in A, go Fx. If it's in B, go Gx. Intersection, 我随便都可以用哦。But is it possible or not? Can you do that or not? No. In general, you cannot. But in this case here, this F and G will satisfy Fx equals to Gx in the intersection. So no need to worry one. If you are in the intersection, you can use the first one, also can use the second one, also can. Because Fx equals to Gx, the value is the same. Okay, no matter you Fx of Gx. Does that make sense? Otherwise, it's not well defined for the point in the intersection. You don't know whether you want to go Fx or Gx. But this condition tells you that either one is okay. They are the same. Okay. Then second thing you need to check is continuity. Right? You need to check that why this map is continuous. I guess away from the intersection, is it easy or not? Okay, maybe you need to be careful with the intersection part. But away from this intersection, right? Maybe open neighborhood away from this intersection. It's just the usual continuity for F and G. So maybe you need to be careful about the continuity here. Okay. Yeah. Okay. 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 I also have proof in the national. Actually, it's quite short, this proof here. But the main takeaway from this testing lemma here is about tasting. So you are tasting two functions together. Okay, 粘在哪里? Where are you testing it? Graph. Then there's no more graph here anymore. Here's topological space. Space. Okay. So you glue at the domain there. Okay, you glue at the domain there, and then your function can glue there. So, okay. Okay. Actually, in algebraic topology, this intersection, the function on this intersection, right, is what we call a germ. So this is saying that at this point, right, the germ of F and G is the same. 什么 germ？ 那天我们讲的 function germ 嘛，那个 germ 嘛，一样的 germ， 那个 germ 就是这个 germ。Okay, so the germ there is like, let's say let's draw the graph that Zhao Shen tell us just now. Let's say the graph is like this. Okay, use this one. Like this, but they agree on the intersection, right? So maybe like this. Okay, use the other color. This color. Okay, agree, then you can paste them together. And this part here, we can call it a germ part. Germ of the function. Okay. Okay, so we are really pasting them because they are equal at this intersection, right? So we really are pasting them together. 把连在一起. Okay, so far okay or not? Yeah. 我要无限靠近，连着的地方无限靠近，什么意思？给我画一个东西给你看。So for example, we can combine this G and F here. So let's say my G looks like this. Okay, and then my F look like the other way. Okay, then we can glue this together. Why? Why can we glue this together? 来问一下石颖。OK， 红色的叫 F， 蓝色的叫 G， 这个 intersection 是0点，为什么可以 glue 在一起？为什么可以 glue 在一起？不要算了，看这边就好。看在合的地方发生什么事情 ？F0 跟 G0 是什么关系？G 在0点是什么 F 在零点是什么？零啊，所以它们两个等于啊，等于比较重要，所以 F 零等于 G 零，它们两个都是零。OK， so you can glue them together, but in the second case, right, you cannot glue them together. So, for example, let's say put a hole here, okay, and then I jump. OK， 你看这个零点就不一样，F 零跟 G 零就不一样。Why you cannot glue them together? Not paste them together. OK， 呀 ，Adrian， 你要讲吗？什么年代？什么很靠近？你说这样 ，Can you still glue them then? Yeah, you can glue them. Can you glue them? Yeah, you can glue them. Their intersection is empty, right? But problem is after you gluing them, is this continuous or not? This is another question. So you need to check two things on being a function and being continuous. We need to check two things. Huh? Okay. Yeah. Okay, but anyway, this is still a good gluing here. Why? Because this point here is easily to be removed. Remove a singularity. The called singularity. Removable singularity. Yeah. Discontinuity. Yeah, discontinuity. Okay. Yeah. Easy to remove. You can fill it in. But for example, this one, if you try to join them together, you don't know how to fill this. 你要 fill 一整条线啊，在一个点上面。in topological space, actually, you can. But okay, later we'll see something called Seng curve. Seng curve. Seng curve. Okay. But we are not using function way to fill it in. We are using limit point way to fill it. It's not a function. Function 不能 fill 你要 fill 的话，你要整条连进去。But can you do that or not? You cannot send one point to so many. Not a function. Yeah, but we can use a limit point. Okay. Yeah. Yeah. So one very important point is these two have to be close. Open. 有关系 because this close meaning the limit point is in there. If you don't have a limit point in there, then probably you will cause problem to your continuity. 会有问题，应该不会 general 对，可以 try 一下，你可以 try， 会有问题。In particular, one way you can think about it is about from the limit point of view， 它会有问题。For example, I mean， 我觉得很简单的 example 应该就是刚才嘛 ，maybe 就这样，这样 ，Yeah， 对吗？有问题吗？这样问题。要 try 一下，要想一下。Okay, I think that's all for continuous function. Okay, so main thing from a continuous function is you need to remember that for every open set, the pre-image is open. That's all. Right? You want to always remember this. Okay. Next, let's go to a product topology. Okay, let's define a product topology here. Okay, so before defining the product topology, right? So let's make some motivation first. Okay, well, how do we define finite products? If you want to define a set, you need to tell me how the elements looks like, right? Okay, so what do you think? How the elements in a finite product set looks like? N tuples, right? Okay, very obvious here. X1, X2 to Xn. But how about infinite tuple, infinite product? going to do infinite tuple, omega tuple. So how are we going to define this dot forever non-ending one? Okay, okay. Or in general, okay, or in general, how do we define, or more generally, we need to define for arbitrary index set. Okay, could be countable, could be uncountable. Okay, anything could happen. Okay, so first of all, let's define a thing called J tuple. Okay, let's define something called J tuple. So just now it's N tuple, right? Now it's the J. So J here is an index set. So given a set X, okay, we will define a J tuple of elements of X to be a function. Okay? Actually, it's a function from J to X. Okay? It's a function. So if you apply to our general case, right? If you apply to our general case, let's say product, finite product of xi, okay? So what's the index set here? The index set here is just 1 up to n. Okay, so when you specify an element here, what are you doing here? You are actually sending 1 to some element in your xi. Does that make sense or not? Okay. Okay. Does that make sense? Okay. So you are picking for 1, you pick 1 element, 2, you pick 1 element, 3, you pick 1 element. It's a function actually. Remember in calculus 2, we discussed about sequence is actually a function. Sequence is a function. A1, A2, A3, A4, A5, A6. Why is it a function? I give you 1, you give me A1. I give you 2, you give me A. It's a function. Okay, so we view the element, this J tuple as a function here. Okay, so we'll define the general Cartesian product here. So let A alpha J. Okay, so let's index our A alpha now. Set. Okay, so the Cartesian product. So the Cartesian product of this index family that's denoted by I of alpha in J of A alpha, okay, is defined to be the set of all J tuples. Okay, for all the J tuple of elements of X, such that X alpha is in A alpha for all alpha in J. Okay, so if we write out in set form, what is it? So let's write it down. So this Cartesian product here is actually all the function, okay, from J to union of A alpha here. Okay, a bit like what does this remind you? Like a choice function, right? Map into union of some set. Okay, you are making choice here. Okay, and that for every alpha in J, X of alpha living in A alpha. Does that make sense? Okay, so if you look at just now here, right? So what is it? Where is this function? This function is going from X from J to union of all the xi. Unit of all the x. And then you have some control on your image here. Each image here need to live in the right A alpha. Okay, you cannot hit from different A alpha. Okay, no? So this is the most general form for your Cartesian product. Okay, you can cover all the finite case. Okay, no? Any class you do Cartesian product already? Any class? MA2 complex or something else? Huh? Did you do finite Cartesian product? Okay. If you do this, tell your lecturer it's actually a set of functions. Okay. It's a set of functions. Okay, so this n double is a set of functions. Okay, so now we define this set already. Now we want to make it into a topological space. Okay, so we want to make it into a topological space. So let's say we started with a bunch of topological space. Okay, let's start with a bunch of topological space. Okay, so you want to ask yourself, if I consider the product space I alpha and j of x alpha, what's the open set here? What's the open set here? You know open set in each x alpha, right? So together, what's the open set? What's the obvious thing you do? 最直接的想法，你会怎样做？知道每一个的 open set 吗？现在我要全部一起，你最直接你会怎样做？中立 Union not quite， 就是拿这个 product 过来。Okay, so we consider this product space with basis of topology as pi of alpha in J of U alpha, such that U alpha is open in X alpha. Okay, for all alpha. 就是你在每一个 component 放 open set. Okay, 这是最直接的做法。Okay, and then the topology generated by this basis is called the box topology. Okay, it's called the box topology. Okay. So you can show that this is actually a topology. So meaning, what do you need to do? You need to check empty set is in there or not. The whole space is in there or not. The whole space is in there, right? Because every x alpha is open. So product of x alpha is one of the bases. And empty set also in there. Then you need to argue actually product of an empty set is actually empty set. Product of empty set, right? Yeah.
What if I have one of them?
You mean one of the S alpha is empty, huh? One of the S alpha is empty. I think you can show that it is homeomorphic to removing that empty set. Then
the result still part of.
What do you mean? So okay, so for example, you mean let's say x cross y cross empty. My point is I think this is homeomorphic to s cross y. And then what do you want to know?
S cross y part.
No, because here what's the open set here must be ux cross uy cross empty. There's only one open set in the empty set, which is empty. Okay, 讲错东西了，好像 cannot Is empty set a topological space? Is that a topological space or not? Wait. So how to think about this? Is empty set a topological space or not? I think can, no problem because it's a subset. Empty is an empty subset. Yeah, should be okay. Yeah, fine. Yeah, empty is open, empty is open, empty and empty is open. Empty intercept, empty is empty, empty unit, empty is empty. Empty space. Oh, you are empty space. Okay. You empty space. Okay, good. So the open set is looking like this in the box topology. Later we'll define another topology on this product space. Okay, this is an open. This is a box topology. Okay, so you can check all the topological property. All right. So next we're gonna define another topology on the product space. So before doing that, let's define something called the projection mapping. 哇，时间过很快，现在要4点了。Let me define product topology and then we take a break. So the projective mapping pi b, okay, is the function. I think you know what I'm trying to do now. Let's say pi beta. So pi beta will map the product space, okay, to the beta component here. Okay, so meaning you send x to just x evaluate at beta. Okay, you take the beta component. Remember, x hat here, you want to replace in your mind as the n tuple, but the n tuple is like can be infinite one. Okay, so it's not precise, okay, not rigorous to do the non-ending infinite tuple. So instead what we do, we replace it as function. Okay, actually this function is already tell you can read every alpha and then get you an x alpha. Okay, so in this case we read the beta component out. Okay, so since we have defined this, let's make some notation here. So sometimes we will write s hat to be like the usual sequence notation, you know, x alpha such that alpha in J. Right, this is the calculus one on an such that n is in n natural number. Okay, so what is x beta then? We will denote it as s little b. It's the b component of element. Okay, does it make sense? This one make sense? Maybe let's recall your calculus knowledge. So let's say n in n, right? Okay, a2 here we project to the second component. Okay, because here you got like a1, a2, right? Okay, so here is like a hat 2 equals to a2. Okay, make sense? Okay, man. Okay, so we're gonna define product topology and then we're gonna take a break. So let's define this SB here. SB denote the collection of all the pre-image. Okay, all the pre-image of UB. Okay, such that UB is open in XB. Okay. Just now we are taking all the open set in XB, right? But now we consider the pre-image of this XB. Okay, sorry, pre-image of this UB. Okay, under project. projection mapping here. What do you think? What do you think how this pre-mesh looks like? What's this pre-mesh looks like? I think you should immediately think about the form of this pre-mesh already. Yeah, let me draw it up. You should immediately think about what form is this already. So let me write that. Okay. So if you have UB here, go backward. What's the pre-mesh looks like?陈月，它 pre-mesh 是什么？什么东西被 map 进 UB 里面？啊 ？U alpha 是谁？隔壁老王。U alpha 是谁？啊 ？Union 又来 Union， 为什么会有 Union 的出现？有谁啊 ？Yeah, here is a J double, right? Must be UB in the B component, right? Because you are reading the XB. But how about the other part? Huh? Everything, right? Every X alpha. Let's say we can index our X alpha. Okay, so let me make a disclaimer here. Let's say, so let's do a disclaimer here. So let's say in the example of J is finite. Okay, if J is finite, then what you have is X alpha 1 dot cross U beta dot until X alpha n. Okay. Does it make sense or not? Because you can put literally anything in different X alpha. After you map, disappear already. So the prim image is everything else except at the X alpha spot is UB. Projection map. You are reading the X beta for the coordinate component. For the other component, you can put literally anything. So what's the difference of this set and the open set that we considered just now? The box topology. Inside the box topology, right? This product have more possibility because you can replace it with different open set. But here, only one spot is a different open set. All the other spot is the whole space. Okay, so this one actually has less possibility. Okay, so we're going to use this to define a new topology. So, and then let X denote the union of this section. Okay, so X is equals to the union of every SB. Then the topology generated by the subbasis. Okay, we'll use subbasis to define it. Subbasis X is called the product topology. So how do you imagine about subbasis? Finite intersection. Okay, so you can imagine that, oh, maybe I got another spot, let's say U beta, this one U beta 1. Let's say here is S beta 1, cross maybe U beta 2. Okay, and then AN. Yeah, correct. Okay, S XAN here. Okay, if I intersect this two, what do I get? I just get U beta 1 and U beta 2 at two spots. All the other spot is still the whole space. Okay, now then this is one of your open set already. Okay, does it make sense? Can you see the differences here? Box topology has more open set than this topology. Okay, this topology will always make sure that there's only finitely many components that you can play. All the other components should be the whole space. Okay, turns out that this topology is more useful sometimes. Okay, so this product topology. And then in this topology, only we will call the product set that we formed just now a product space. Okay, so if in literature, when people talk about product space, it's always this product topology. Okay, it's not the box topology. Okay, if you read a lot of text, when people say about product space, it's always referring to product topology, not the box topology. Hey, hello, 金盛，睡茶，金盛。啊，这样时间。Okay, so can you see that which one contain which? Which topology contain which? Any topology contain which? Let me see. Okay, never mind. We are not comparing it. Okay. Okay, let's stop here first. Any questions? Any question? Can discern between box topology and product topology? Why? Not very rigorous. Which part is not rigorous? This is a very serious education. Yeah. So one is about bases, one generate using bases, one generate using sub-bases. But both of them, the element they use to generate is also different. Sub-bases. Yeah. Sub-bases. Correct. Correct. Because we need to decide what sub-bases we need to use. So this is the sub-bases we take off. So meaning the element that we consider is of this form. So inside this X script S here, all the elements is in this form. Why is it union? Because you look at different beta. You take all the possible U beta cross with different X sign. Okay, but the result of finite union is you can create things like, okay, so let's say if I intersect these two, right? Okay, if I intersect these two together, okay, let's say I intersect these two together, what do I get? Actually, I get X alpha 1 cross up to U beta 1 cross U beta 2 cross blah 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 until Xn alpha n. So what we introduce is we only have finitely many components would be a random open set. For the rest, it should be the whole space. Then this is different from the topology we had just now already. The topology we had just now is what? I can put any open set in every spot. But here no. Only finitely many. Because finite intersection, right? What do you mean? Dividing this space. Huh? More component? Why do you think more component? I thought the previous one has more because the previous one you could have different U alpha I. Yeah, more fine. Which one is more fine? Which one more coarse? Which one is finer? Which one is coarser? Box is finer than product. Yeah, because every open set in the product project is an open set in box. Box is more finer. Box or another box is larger. Yeah, because box is okay, 分得更细。Yeah, Okay, very important. Okay. Okay, makes sense. Okay, okay. So let's break until 422. 422. Come on.
不一定啊，可能有两个，不过它可以有两三个，那我哪一个？那我那个里面我那个看起来很奇怪。
那一 man 一，你可以把它 replace 小的 open set。
Although in fact equal to A union, then open is the same for have closed. Then one is open, one is closed. That's the example of the function. If both open as open as to A union B, then the inverse image of U is inverse using F and union inverse using H. Then it both open, the union is open.
Okay.
Yeah.
这样啊，无所谓。你有快的问题吗？
没有，你not 的问题。
OK，你要问还是你要发给我？你发给我，你发给我，你跟我讲什么错，我看一下。
啊，你自己讲的，union 跟 U 分不清楚。
怎么嘞
？union 跟 U 分不清楚。
哦，因为，OK，我也不要因为他，但是就是说 like，因为不可能两个 U。
对对，我知道，对，所以我刚。
我也是
看不懂的，然后我跑去看他们写的情况。
没有，他不可能会两个 open set 存在一起。
对，
对，
我就觉得奇怪。
在这里写。
Yeah, we use closed definition. If you
open, you use open definition.
Open also work.
Let me think.
Yeah.
所以有没有什么其他要求？哦，会有 limit point 的东西影响。
We say that X equal to A union B, so we already let the limit point go into the intersection C. Because the whole space equal to A union B. This. Yeah.
Okay, I think there's one more issue maybe you need to be careful. So I think it's about function. Okay. So let's say it's open. Like this. Okay,
Yeah.
so meaning your function actually not defined on this point. And then this function also not defined on this point. But maybe you will say that, oh, they agree. Actually, they agree on all these. Oh, they agree on all these. That's your problem.
No, because the continuity says that it can jump at that point, which is not defined.
Let me think. So, okay, I think there's some technicality I think need to address here. Let's say your one.
既然只有两个东西，为什么要四个有线
？Yeah, so if you pass by this point, the limit is the same. And then if you pass by this point, okay, maybe if you use open, you need to consider this kind of thing. Right? You need to use continuity to help you to cover this kind of thing, to make sure that. What do you need to make sure? Because if it is closed, you won't have this issue. If it is open, then it is not clear why. It's not clear why. It's not clear why this point here will fit. Okay. Well,
but the continuity.
For example, yeah. For sure, the continuity will give this. But when you try to write down, this is it. But when you try to write down fx, right?
Yeah.
So how do you write this down? Okay, I think you will write it as let's say this is F, this is G, right?
Yeah.
So I think you for sure you write fx equals to G, fx equal when fx x is a, so x a, then is x equal b. But I think because you cannot straight away use fx equal to gx on the intersection anymore now, because at this point you need to check separately these 2 points.
Yeah.
I think a bit more troublesome. But I think it works, but you need to check it. But you still need to check it.
We just simply use the definition of continuous by open sense，对，这是 clear。他为什么？就是
你刚才讲
两 A 跟 B 都可以，
可以，但是你看，它有一个地方你要检查，就是这2个点你要检查。比如说，
这2个点如果是 open 的，不是根本就不在里面吗？
我想一下，没有，你拿他们2个的 union 吗？
Yeah.
这一个 interval 会包掉这个点，这个 interval 会包掉这个点，所以它补齐了那2个 open 的点。
去 check 一下，但是我觉得应该是成立。
是成立，但是我是讲要 check。如果你用普通 continuity 来想是成立的，但是要 check 吗？因为你不能够直接用这个条件啊，这个条件不会 work 在这2个点上
我懂你
所以你要检查。
对
应该是 work， 但是你要检查这2个点。其实你要检查是 function 的问题，而不是 continuous。continuous 可能很容易吧。
Actually， 很容易，然后就是 well defined 就是。
对。
为什么会有 well defined？
应该也是 continuous 的问题的，是 continuous 来的问题。
continuous 的话，continuous 很简单，但是如果 well defined 的话，这 continuous 很简单。
不应该是 continuous 问题。那我想想 ，function defined
的 well defined 的问题。
不是，如果没有 well defined，不是没有。
我觉得是 continuous 的问题。因为 function 已经 define 出来了。
哎，你去读你的 proof， 你把那个 proof 里面所有的 closed 换成 open， 你就会发现它就可以了。
但是问题是，可能我没有检查给你看的是为什么 F 是个 function 啊？
我觉得不用啊，为什么它不 well defined？
因为我觉得这个不是一个 trivial 的东西耶，我感觉这不 trivial。
我先有1秒钟问个奇葩问题，你刚刚说 open neighborhood 为什么不一定是 open set？ 你定义 open neighborhood 的时候，你会定义 open set？
给我想想。如果它是 open set， 为什么我要定义 open neighborhood？
因为 open neighborhood 是 open set 的 contains。
OK。
所以你刚刚说 open neighborhood 不是 open set 直接包。
我一直想什么？对，
有些书上有定义 neighborhood 这个概念，我就不确定 neighborhood 跟你这边 neighborhood 它有点 difference。
没有书的 neighborhood 跟我的 open neighborhood 是一样。
有些书的 neighborhood 不一样。有些书的 neighborhood 是它可以不 open， 但是它包括一个 open。
对，我一直在想这个东西。
对，
所以我说 open neighborhood。
你的 open neighborhood 应该只是要 open 的。你都加上 open neighborhood 了，它不 open， 你不觉得很 ridiculous 吗？
对，我觉得你讲对。对，因为 matrix space 那个 neighborhood 确实就是不 open， 不一定要 open。neighborhood 那个 open 那个 matrix space， 所以我才把它分成叫 open neighborhood。
对
，OK 好。叫 open neighborhood 在我的课其实就是一个 open set contain 一个东西。
对
，neighborhood 只是要告诉你说它是某个它 contain 某个。
一般说的 neighborhood 是在说它是一个 set that open。
对，我就是要区分那个东西 ，matrix space 里面有这个东西。OK 啊，
去 check 一下，我觉得是可以的。
我觉得是可以的，你签。
我觉得如果
应该是可以，
觉得可以去参考你那个 close 的
proof。没有，我觉得我那要证什么啊？
没有，
我要证的是这个。
这一整段一定是活在其中一个排 function 上的，所以它在这个点就 continuous。
没有，但问题是我们要让它跟 G 的地方连在一起。F 肯定它是 continuous， 但是这个点加进来过后 ，G 是不是在这个点 continuous？
但是本来 G 在这个点没有定义啊。
G 这个点没有定义，所以我现在要考虑的问题是什么？
你在这一段都已经接上了以后，那其实你在这个点，
我还不知道有没有接上，我现在就是要证明它接上。
你中间那段一样，对不对？
对，
在这个点你可以用 F 来接，那个点你可以用 G 来接，就不
对，但是我现在要证明的是，
那你为什么需要？
我现在要证明的是 G 接过来真的是接到这个点，
为什么一定要
啊？不然的话，可能 G 这样子出去呢？
不可能啊，
就是要用 continuity 说它不可能。我的意思是说，我就是
好的
continuity 说它不可能，
I see.
对不对？它不 continuity 它就跑上去了嘛。但是我们就是要让 continuity 让它连接。哦，OK，should we discuss this？ 几点了现在？喂，12。Okay. Just now, there's a very interesting question pointed out by Eric, right? And then Soning tried to solve it also. So the discussion that we have met just now is, let's say you take a union of two open set like this, right? Okay. And then you define F and G on A and B like that. Okay. But what's the problem here? The problem here is if you look at this continuous G here, right? If it's open, then you don't have definition on the endpoint. Let's say this is a R case, okay? And then if you have a F definition on A here, you also won't have definition on the endpoint also. But we try to prove that the pasting lemma also work on the union of these two open set. Okay, so meaning there is a way to fill in these two undefined spot. Why? Because you can see that the undefined spot for G actually is defined for F. So we try to argue that we can fill this point using the F point. And then similarly for the G point. Now the point is, why is it continuous then? For example, well, obviously, if you fill this for F, F is continuous there because it's coming from F. But if you consider from G, why after you filling it in, this spot is continuous for G part. Similarly, for the other counterpart here is, why this point is continuous for F if you fill it in. Let's say if it's not continuous, if it's not continuous, G obviously might go different limit, right? Okay, let's say use the epsilon delta to think about it. You should go to the other limit. Then you cannot just fill in this point. But the point is this cannot happen. Can this happen? This cannot happen. Maybe you need to do some contradiction on this intersection part together with the continuity. Only it works. Yes. Yeah. You cannot simply say, oh, agree on intersection. And somewhere around this endpoint here, maybe the G go up a bit. You cannot. I think you somehow need to use continuity and this intersection property here to get a contradiction so that you can feel it continuously. I think it's a very good exercise. You can try this. Okay. Yeah, quite can try think about it. Okay, so let's quickly write down a theorem that I already keep explaining to you just now. Let's compare box topology and product topology. Let's explain this two topology here. So what's the basis? Okay, basis of box topology here. This is as what we have discussed just now. You just take product of U alpha. Okay, such that U alpha is opened as alpha. Okay, and then second, basis of product topology. Okay, actually you can write it as, instead of writing it as a union of finite intersection form, what we're gonna write it is as a more sophisticated way to write it. So also pi alpha of U alpha, but it's not the same thing. It will say that U alpha is opened in X alpha for all alpha and U alpha equals to S alpha except for finitely many value of alpha. Okay, a bit confusing, but this is a standard way to write it. 读得懂这句话吗？ Okay, this is the standard way to say what we draw just now. U alpha equal to S alpha. Okay, almost everywhere except for finitely many value of alpha. 除了 finitely many of them 不是 ，OK， 其他地方都是整个 space。OK， except finitely many。OK 吗？都是 except finitely many。OK，so this is the way how we describe the topology that generated by the subspaces that we have drawn just now, which we use the pre-image of the projection, okay, of U beta. Okay, so well, let's make a remark here, very quick remark here. If you are considering finite product, actually both of them are the same. Okay, if you consider just finite products, actually box product is equal to product topology. They are the same actually. Okay, if your product is just finitely many. But in general, box topology is finer than product topology. Okay, it will contain product topology. So in general, we will use product topology. Okay, later we will see why is it better to use. Okay, few examples you can draw is, I don't want to write down the whole statement. So a few examples you could draw. I don't even prove it also, so you don't need to care about the proof also. So our first theorem is a product of basis elements is a basis element of product space. Okay, does it make sense or not? Okay, like what we do just now, right? We take product of open set, make it a open set in the product space. So now it's a basis element. No? Look at the smaller constituent of your open set. Second is product of subspace. Want to guess what's the next line? Yes, line. Product of subspace is what? Is a subspace of product space. Yes. Okay, so if you take a bunch of subspace together, take a product, then it becomes a subspace of your product space. And then third one, so this one is second one. Third one, if you take product of Hausdorff space, what do you think? Is Hausdorff. Okay. So meaning what? If you have two open sets that can separate every point in your S alpha, right? If you take product of them, it still can make up the open set they can separate the two tuples. Okay, I think it's like that. I think the proof is immediate. It's not tricky, I guess. So that's why I don't include it. Okay, last one, more interesting a bit. No, not the last one, but the second last. So fourth one, product of closure is a closure of, it's a closure of a product space. Okay, so if you take pi of A alpha bar is equal to bar of pi A alpha. Okay, last one. This is the only one that only works for product topology. Okay, so theorem 5 only works for product topology. So this one will distinct product topology and box topology already. So the last one says that product of continuous function is continuous. And the other direction is, if you have a continuous function and then you look at the components, is also continuous. So there are two directions. Okay, you take continuous function can build a continuous function, build a product of continuous function, and then if you started with a function, continuous function on your product space, the component itself is continuous. And this only work for product topology, not box. Okay? Actually, we have examples. Maybe we don't prove this also. We look at the counter example for box, coming from box. Okay, so let's see how this theorem fell in box topology. So this is telling you why box topology is not very applicable, not nice, not practical. Okay. If product topology, it work well with continuous function. Okay, let's try. So we're going to define a function from R to I alpha and R here. Okay, so what's this map here? This map is really straightforward, just sending T to a bunch of T. Okay. So, well, T go to T, right, should be continuous, huh? Yesterday discussed about this. Wait, okay. T to T 为什么 continuous 啊？对，把 T 送去 T 为什么 continuous？T 送去 T 是什么 function 来的？有变还是没有变？对 ，T 送去 T 有变还是没有变？没有变，不是没有变的 function 叫吗 ？Identity function。Okay, identity function 是 continuous 的。Okay, but I'm gonna prove to you that this function is not continuous. 不 continuous。每一个 component 都 continuous， 放在一起就不 continuous。Okay, if we consider this product set as a box topology, okay, we change the topology here, okay, as a box topology. It's not continuous. So how to show not continuous? In where the product set, okay, and then look at the pre-image. It's not open. Okay, so let's take some open set here. What open set we should take here? A very open set we're gonna take here. Sorry, a very clever open set we're gonna take here. So let's consider this open set. Okay, let's consider this clever open set here. -1, 1. Okay. Negative half, half. Negative 1/3, 1/3. And then blah, 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 blah. Okay. So this set here will contain what? 0, 0, 0, 0, 0, 0, 0. Okay. What am I doing here? Can you see a pattern here? 1/n. If you are an analysis student, right, you must be sensitive to 1/n. What does 1/n relate to? 1/n. Okay, relate to 0. There's some property, right? Archimedean property going on here. Okay, so what are we going to see here? So if F inverse B is open, means what? It should contain some. It should contain some open interval. Let's say minus delta to delta, because this is a basis element in R containing 0. Okay, because 0 sends to 0 is one of the pre-image of this basis element, right? Okay, so which means F of minus delta to delta should be living inside B. But could it happen or not? But what do you see here? If I look at the image of this minus delta, delta, what do you get? Minus delta, delta in every spot. Minus delta in every spot. Because you're sending T to T. So surely you send this minus delta to all the minus delta to delta. So meaning if you look at the each projection, you will see that minus delta will live in pi n. For all n, is it possible? No, right? Because for some time, 1 over n must decrease until you're smaller than the delta. This is Archimedean property. You will always find a n such that 1 over n is less than delta n. Okay, so these will violate the Archimedean property. Okay, so you violate the Archimedean property. Right? Because Archimedean property tells you that there's one n such that delta is greater than delta is greater than 1. Yeah, so that this one will contain. Not always containing. Okay. Yeah. Okay. Okay. For this last half hour here, I want to talk about something that's not in your exam, any exam, final or midterm, but I want to talk about it. You don't need to copy also, just listen it as a story. Actually, it's pretty important. Maybe you will see it in algebraic topology later. So something called a quotient topology, 对吗？哎，我们在 group 也是这样嘛。We define product group 先嘛，然后我们要 define quotient group 嘛。Similar here, we also need to define quotient topology. Okay, after product topology, 加减乘除一定要学好了。所以加跟减在 set 里面是什么啊？ Yes, union and intersection. Okay, then we learn product topology. Now we learn quotient topology. 加减乘除全部要学好了。Okay. But the proper treatment of this section here will be algebraic topology. Okay, hopefully you can do algebraic topology later. 有在画饼。Okay, let's continue. So let's consider two topological space. In a group, what do you start with for quotient group? Yeah, sure. Other than coset. First isomorphism start with what? Yes, surjective map. Similarly, here we also consider surjective map between topological spaces. Okay, so we must start with a surjective map. And then we call this map a quotient map. We call this map a quotient map, provided a subset U of Y is opened in Y if and only if P inverse U is open in X. What did you observe here? Based on what you have learned, what did you observe here? This requires the pre-image of U is open. And also, if P inverse U is open, then U is open. So this one is stronger than continuity. Continuity only will go one direction, but here got two directions. Okay, this is stronger than continuity here. So sometimes people call it strong continuity. Strong, yeah, strong. Yeah, strong continuity. Okay, similarly, you can rephrase it as close. Okay, if U is close in Y, then the pre-image is, if only if the pre-image is closer. Okay. What else? And also you can see that this condition is equivalent to homeomorphism, right? Okay, so actually homeomorphism is a bijective quotient map because homeomorphism have inverse. Okay. Yeah. Inverse plus this if and only if condition here. Bijection, I mean, yeah. Okay, so homeomorphism actually is a bijective quotient map. Okay, so let's see how we build this quotient topology. So we're gonna write a theorem. Although it's a definition, but if it requires a checking, so we write it as a definition, theorem. So if X is a topological space and A is a set, A no need to be a topological space. And if P to A, P from X to A is a surjective map, then there exists a topology on A. Okay, so meaning I don't need to start with a topological space A. Okay, I just have a topological space X, and then I surject to A. Surject to A means what? Every point in A has a pre-image. Then you can use this pre-image to talk about open because you know the openness in X, but you don't know about openness on A. So how to define it? So we define the topology on A relative to which P is a quotient map. So let's say P is a quotient map. Let me see. P is a quotient map. Then P is a quotient map, then you require both of them to be topology, right? Oh, okay. So actually they try to ignore the topology on Y. Okay. So okay, so let me write down first. To which P is a quotient map, it is called the quotient topology induced by. Okay, so maybe I need to tell you how we define this. Maybe I leave the checking for you later. So how do we define this actually? So we will declare that. Actually, what do we do is we declare U in A open. Okay, if P inverse U open. Okay, that's it. Okay, so we can do this because we have a quotient map here. Okay, so when we write down the quotient map, right? Just now when we define quotient map, we need X and Y both to be topological space. But here we didn't mention about topology on A because we're going to define new topology on A. So this is called a topology on A relative to this P. Okay, so this is a new topology. Okay, induced by this quotient map. Maybe A on top of A, there's a topology set, topological space. Topology. But now we define a new topology using this P here. How to define open in A now? Maybe A can have a set of topology, but we don't care. We define a new topology there. Okay, yeah. Yeah, we are defining new topology. We are defining new open set. Yeah. So we declare a set in A to be open if the pre-image is open. Yeah. Because we have this P to be a strong continuous function. Okay, so we will know when P inverse U is open. Okay. Later, I'll give you a very nice example. Or actually now, let's see. Yeah, actually now. Okay, so I got an example here. So for example, let's define this surjective map here from R to A, B, C. Okay, so how do I define this map here? So what I do is, there are 3 points here, So how do I decide who goes to these 3 points? Okay, though very easy description here. So I split this real line into 3 parts. Okay, something less than 0, something greater than 0, something 0. There's only one thing 0. Okay, so what I do is I send positive number to A, send 0 to B, and then send negative number to C. Okay. So what's the topology I define here relative to P? This is a let's say 3-point setup A, B, C. Okay. So I already described to you, right? In this world, up to computation, there are 9 kind of 3-point set topology. So which one corresponds to this one here? And how to decide? You need to decide if you have a subset of this 3-point set is open if the pre-image is open. Yeah. Right. So name one try. Can you give us the first one? A. So you say that this set is open, no? So you need to look at the pre-image of this set. No? Pre-image of A is what? Who gets sent to A? 0 open interval from 0 to infinity. This is open in R. Okay. Can you pick another open set? Huh? AC, huh? Okay, AC. What happened to AC here? So what's the pre-image of AC? Who gets sent to A and C? Everything except 0. So negative infinity to 0, and then 0 to infinity. But this is the union of 2 open intervals. Still open. Okay. Anything else? C. Okay. The reason for C and A is the same. Similar. Cannot say same. Okay. Okay. I purposely pick the right color to match the open interval. Hopefully you can complete that. Okay. So this is the topology, the quotient topology on A relative to P. Okay. No? Does it make sense? Because in this topology, you can literally put 9 of them, right? Any 9 of them. But the one that corresponds to this P net here is this one. Okay, it's this one. Okay. So this is quotient topology. How many times? Whoa, 哎呦，很好玩呢，来不及了。Ding ding。OK， 再给我5分钟，再给我2分钟。OK， so let x be a topological space， 感觉有点疯了。Let x star be a partition of x, partition of x into disjoint subset whose union is x. So this is like your assignment 3. Assignment 3. Okay, so you define a partition of x into disjoint subset about the set of line in Rn. You define the pseudo metric, right? Okay, you break your Rn into set of lines, right? Okay. Sorry, 我写什么 ？Okay, 切掉。Okay, let P be a surjective map. Okay. So meaning we send x to some x bar that contain x. 这样子写 OK 吗？ Yeah, I think OK. Okay. Then in general, whenever you do this, this is really general. We can define the quotient topology induced by P. Okay, and then the space x star is called the quotient space of x. Okay, this is really general. This is really general here. So you start with x, a topological space. 随便切，你自己切啊，你想怎样切就怎样切。As long as it's a partition. So meaning what? Between these partitions, the intersection is empty. This is the only thing you need to confirm. Okay. then you will have a quotient topology on your X star already. Okay, about yeah. Okay, so this is defining on the topological space. You have a topological space, depend on how you want to partition it, and then you will get a quotient topology here. A very nice property is this one, not property, example. Again, nice example is this. If you take a closed ball here, so closed unit ball. So this closed unit ball is just inside R2, no need too big. So it's an X, comma Y in R2 such that X2 plus Y2 is less than or equal to 1. And what's the partition I want to do here? So what's the partition we want to do here? So I just need to tell you what are the set here. So what are the set here? The set here is boundary of this ball and every point in the interior. Okay, so what I do here is if I draw this ball, unit ball like this. Okay, what I do is I treat every individual point in the open ball as one point, and then I identify the boundary. I identify boundary mean what? All these boundaries become one point. Actually, 你的纸可以借我们，可以折吗？可以拿一个可以折吗？对对。So if you identify all the boundary, what happened here? 全部 boundary 给它连在一起。Yeah， 连在一起。We treat as one point. 变成一个圆圈。Very good. 变成一个圆圈。So in mathematics, what we meant here is we claim that X star is actually homeomorphic. Okay, homeomorphic to S2. Okay, so S2 is a unique sphere. Okay, in R3. 变成一个圆圈。这个圆圈是活在 R3 里面的。Okay, but you see here, maybe 你会看到这个形状变了。But now we fix the radius to be 1 because we just need homeomorphism. Okay. Yeah. 有点深刻。好像你包，你要包肉粽怎样包出来的？谁知道怎样包肉粽？你一定要揉那个面团嘛，揉了那个面团是揉压成这个形状先，然后你把肉放在中间嘛，那你把上面不是 identify 起来拿去蒸才有一个肉粽你不是肉粽，所以肉包，对吗？就是这样讲，就是这样讲。Okay, so you identify all the boundaries together, become a point, then become a sphere. Not just circle, this is a piece of inside is filled in one. Yeah, this is a closed ball. It's not just a piece. Sorry, yeah, it's a piece. It's a closed piece. Okay, it's not just a circle. Okay. Yeah, I can think about this. Maybe this proof actually quite nice. I draw it up. You can have a read. If for chance, maybe I share with you next lecture. It's quite technical. This proof. This proof is a bit technical. I won't test this proof, but just give you an idea. Okay. Any question? Any question? So homeomorphism means what? There's a bijection. And then the forward map is continuous. Inverse map is also continuous. So I need to produce this map. I need to show this. Okay, any question? Any question? Any other question? Any question? Hey, are you interested in how we prove this? So what we prove this is use B2, right? Homeomorphic to R2 first, Okay, and then homeomorphic to X2 take away a point. Okay, and then only then we union back the boundary stuff. The boundary stuff will get sent to this special point here, 001. Okay, so 我们用一个 open disk. Okay, we take an open disk. The idea is we take an open disk, and then we show that it's homeomorphic to the R2, the whole plane. And then we showed it to a, this is equal to a sphere without point. Okay, and then we put the boundary back. So we put the boundary back. Sorry? What do you mean? Oh, you mean if I exclude all these other points? You can exclude any one of the points. Just that this is a north pole. So we can, I mean, this two relation, can you guys guess or not? I think you guys use it in your assignment 1 already. This is the stereographic projection. 从哪里？从 north pole 开始啊。Yeah. Okay, so how about let me show you the picture 啦。等下你回家睡不着，可能我睡不着。Okay, so the picture is like this. You can use this picture to show openness. Okay, so there are two open set you want to consider here. Two kind of open set. And then you can see under this homeomorphism what this open set becomes. Okay. So you can see that this open set becomes this open set here. And then say as an open set here. But if you see an open set around your boundary become what? It becomes another open set that include the infinity points here around R2. And then move to here, it's just an open set around North Pole. Because you put your boundary, later you need to map your boundary point to this North Pole. Obviously, it has to stay around North Pole. This is what continuity means. After mapping, it still stay around the image. This is what continuity means. Okay. Yeah, you can read the proof, but I summarize in this picture. Okay. Yeah, the proof is quite technical actually. I'll tell you one step we need to use stereographic projection. Okay. And the other step, I think, not too hard, but I think the other step. So this step is this, a bit like calculus thing, calculus 2 stuff. How to pull your open ball into infinity. Why do we need to glue the boundary? No, this is just a construction. Just to tell you that if we glue the boundary point, it builds out a very nice mathematical object here, which is a sphere. So you can use close this to build a sphere. 3 sphere. 2 sphere, sorry, 2 sphere. That's 2 sphere. Okay? 2 sphere in R3. Okay? And then by this, I think we finish topology section. We finish. Yes. So next week we will start connectedness and compactness. Good luck all. See you next week. 对。